So, to recap, things starting to get crazy here, right? This lecture's version, what I call multivariate regression, is done that way because none of the dependent variables or endogenous variables predict any other endogenous variables in our model. So I made this distinction between multivariate regression and path analysis. More generally, path analysis is where you can have some of the endogenous variables predict other ones. And the reason I'm making that distinction for you is to sort of slowly introduce all these things without completely overwhelming you, like infinitely overwhelming you, only just moderately overwhelming you, or so. But part of that is when you have a model where the endogenous variables don't predict other endogenous variables, you will not have any indirect effects. So there's going to be no indirect effects today in our analysis. No mediation here. We do have moderation. We have interactions present, but we don't have any mediation, which is the presence of indirect effects. Cool? Cool. Awesome. So this is the path diagram that I made in PowerPoint, which takes like forever. And this is the quick path diagram that I made in the SEM plot package in R. And it clearly looks a lot worse. Even got FML here, whatever the heck that means, right? Seriously. Yeah. Way to go there. FML predicts perf. That's right. Yeah. So the path diagram from R, there are probably better ways of doing that I haven't found. I know that there's a package called Diagrammer, which is really cool that I was trying to get into, but I couldn't find anything that worked directly with Lavaan, but I'm pretty sure people have done it. I just couldn't find it. So you might be able to find better things out there than I've found. So I wouldn't just rely on R's use of it completely. But it tries to give you the same type of picture, though. You see the boxes represent variables in the analysis, even FML. And the arrows are either one-sided or two-sided, right? So it tries to do the same thing all together. There we go. So labeling variables, endogenous variables are dependent variables, are performance and usefulness. Exogenous or independent variables are female, college experience, and the interaction of the two. So now we can do this in Lavaan. Let's go over to R real quick. So backing up to try to talk about Lavaan for a second here. Lavaan is a package in R that is really mirrors, I think it was built after and really mirrors a piece of software named M+. But the nice thing about Lavaan and M+, in that matter, is that it's a very direct way of modeling your data. So I have a data set here, and once again, the format of the data set is nothing different than we haven't seen before. Like next week that changes, or the next topic, the mixed models, it sort of changes. So it gets really crazy. But you can understand this in that each person has one row of data, right? And so that every value for each variable on that row comes from that person. So person ID 1 here provided each of these different scores that we see right here, right? So Lavaan works by means of a very big quote, very big character string for its syntax. So remember in LM and in the CLM package that I introduced you before, you had to create a model formula where you had y tilde x. The way Lavaan works is it takes that formula and plugs it into this big long set of quoted string of syntax. So what you see here is I'm creating a new variable called model1 syntax. And the very first thing that shows up after the equal sign is a double quotation mark, right? Quote mark there. When I run all that in RStudio, all of everything that goes inside of this quote right here becomes one big long character string saved in the model01.syntax variable. This is not the analysis. This is not going to give us numbers, but if I show you what this looks like, this is what shows up. clearly that's great. If you want to try to interpret this, the /n represents the carriage return or an enter, right? So you see enter means, or a better way of doing this, if I do a write.table, and I do model01.syntax, it's just text. That's all it's showing us right here. Right? So writing.table just turns all the /n into enter space. You know, people where you hit enter in your text. So let's go through it. We build a model through this syntax right here. I'll come back to that in just a moment. But then when we take that syntax, we submit it to a function called SEM, which stands for Structural Equation Modeling, which is the package that really Lavaan is. This path model is a type of structural equation model. Blah, blah, blah. It's just lots of words. It's word festival here, word party or something. Not quite, it's almost like word salad, but not quite. Model 01 syntax is submitted first. You tell it the data set. And these other two options I'm just asking you to show up all the time. One is mimic equals m plus, because a lot of what we see, a lot of people use m plus. I just like to use it for that reason. I like the mimic. You don't have to put it there in your life, but just, you never know when someone's going to be like, well, m plus said. And then the second one is estimator equals MLR. That was a topic of one of the lectures that was online before this week. When we put MLR in, what does it do? Does anyone remember from those lectures? Gives you an extra column, yeah. That's right. So MLR stands for maximum likelihood robust. Robust maximum likelihood provides a little bit of insurance if your data aren't quite multivariate normal. That insurance policy comes in the form of kurtosis, remember like the peakness of the distribution. So if your distribution's a little more peaked, if your data are a little bit more peaked or flat than what multivariate normal would say, it tries to adjust the results based on that. So it's a good thing to have. The nice thing about it is if your data are completely perfectly multivariate normal, then it doesn't adjust anything. It sort of goes away. So it's not like it's costing extra to do, so we're just going to put it in there. One thing I will note is it doesn't fix things like I've got a five category variable that I'm pretending is normal. It's not going to fix that, right? So that's how we submit it. Let's talk about the syntax itself. You may see this line right here. It almost looks the same as that model statement that we had in our LM function. We put a dependent variable. We put a tilde. We can put a 1 there. That represents an intercept. And then we put pluses separating each of the variables. Now you'll note in front of each of my variables I have a 0 and a star. What that does is it says if it wasn't there, if I take this off, it will estimate a beta weight, a direct effect of that variable. So we would see a direct effect of female on performance. But this first model, I'm going to have an empty model. We're going to have no predictors in. And so what I'm going to do is actually put a 0 there. And the reason for that is when we put predictors in the analysis in Lavaan, they become part of the likelihood function. So even though they're exogenous, they're not being explained, they cause the likelihood function to go from just 2 variables, which we would have in an empty model, to 5. Which is a little bit weird, but it's how Lavaan works. It's how Lisrel works. It's how Amos works. M plus can do it differently. But why that's important is if I want to do a likelihood ratio test, if I want to test simultaneously whether or not a model with these direct effects is more, if one or more of these is significant, to make the likelihood ratio test, I have to have it work. I have to have the same variables in the likelihood. And because Lavaan puts the exogenous variables in the likelihood, that means our empty model, we have to have all of our predictors in that we know we're going to put in there with zeros in front to make the empty model work. A little weird, right? We don't expect the empty model will fit the data very well, but we just want to start out with a basis for beginning. So once again, the model for the means, with the exception of the 0 star, this is what you would see for each variable in the LM statement. I just have more than one now. One for performance, one for usefulness. Where the Lavaan syntax starts to get very, very detailed is that every part of the multivariate normal has some type of syntax form available to you. What do I mean? Well, this next line, the next bit of this, by the way, this is all optional. If you don't put it in, Lavaan will estimate most of these anyway. I put it in just because I want to make sure I know what Lavaan's doing. Sometimes it shuts things off, sometimes it doesn't. But if I want to talk about the residual variance of performance, I can talk about a variance of a variable by taking that variable and putting 2 tildes in between it. So performance, double tilde performance, tells Lavaan, hey, estimate the residual variance of performance. It's probably going to do that anyway, thank you, but I wanted to be explicit, so I put it in there. Same thing with usefulness. Usefulness, double tilde usefulness, tells Lavaan, estimate the residual variance of usefulness. Ta-da, we've got it. So the covariance gets a little bit more interesting. One variable, double tilde the other variable, says estimate the residual covariance between these two things. And that's where actually this starts to get a little weird. I don't remember Lavaan's default. I probably could check it real quick. But if you don't add this line, it may not automatically add the residual covariance. Sometimes it depends on which program you're using. And sometimes they show up and sometimes they don't. And that's what gets maddening. You need to know what's in the model to make sure it's working the way you want it to. So you have to have this very detailed accounting of what goes in to make sure what you're saying is accurate when it comes out. So, once again, model for the means, that's where basically our regression lines are, right here. This other part, pretty standard. Just put it in. These are endogenous variables. We want their variances and covariances. We put all that together. We submit it to the SEM function. It takes a little bit longer to run, but then when we get the summary statement, now we get all this extra information coming out. And this is where we look under the robust column for our results when we put MLR in. So, there we see it. So, Lavaan is constructing a model that considers all 5 of the variables. So what Lavaan is doing here is it has a model where if you go down to the results, you'll see this here. Actually, you won't see it. We have our intercept for each line, intercept for usefulness, intercept for performance. We have our residual variance, but this is an empty model, so this is just our actual variance of our variables in our data. We have a residual covariance. Then for each of the regression parameters, these would be the slopes, where these would show up. We have 0 values because we set them to 0. And the way that we know they've been set to 0 is that we don't see a standard error, z value, or p value for these. That tells us, yeah, I fixed this to 0. So don't even look here. It's 0 by default, by our choice. But the rest of the model, where we start to calculate degrees of freedom from, comes from the counting of parameters. So here's where we get that degrees of freedom. In this analysis, what Lavaan is doing is actually fitting 3 different models simultaneously. I talk about this in the absolute model fit lecture that was online before spring break, so you can go back to that to revisit it. I'll tell you briefly now. The 3 models are the one we specified in syntax, the saturated model, where every mean, variance, and covariance gets estimated, and the model that has every mean and variance estimated, but a 0 for all the covariances. And so this first model fit statistic here is the model fit statistic comparing our model to the saturated model. Right? The saturated model, again, every mean, variance, and covariance estimated. Our model has whatever parameters. So this degrees of freedom will be the difference in number of parameters between the two. So to count the number of parameters in the saturated model, we have to think of how many variables are in that model. And because Lavaan puts all the predictors, all the endogenous and exogenous variables into that model, we count all of them. We have 5, right? We have performance, usefulness, female, college credit hours, and then the interaction of college credit hours and female. So there's all 5 right there. So that means we'll have 5 means, 5 variances, 1 for each of the variables, and then 10 covariances. V-A-R-I-A-N, yeah, that's right. So there are a total of 20 parameters. Our model has 5 intercepts, even though we don't even see the intercepts of the exogenous variables. 0 regression slopes. We have 2 residual variances, 1 for performance and 1 for usefulness. 1 residual covariance, which is the covariance between performance and usefulness. And then we have the 3 variances and covariances of those exogenous variables. So our model has 14 parameters in total. So saturated has 20, our model has 14. Remember the discussion we had when we got to maximum likelihood and I talked about nested models? The cool thing about path analysis and multivariate regression is that every one of our models is nested within the saturated model. So when we this set of statistics that we see first here is the likelihood ratio test for our model, which is the null hypothesis, like the null model, versus the alternative model, which is the saturated model. Right? Because the saturated model is the data. Nothing can fit better than it. I should say nothing in this class with this type of distribution of models can fit better than it. There are actually probably better ways of fitting it, but let's just leave a little headspace for that if you're not already full of me running my mouth too much. So, our model is the null hypothesis. The saturated model is the alternative hypothesis. This is the test statistic, 22.204. That's chi-square with 6 degrees of freedom. So the p-value is very small. When we see a p-value like that, we reject the null hypothesis. So we're rejecting our model. It does not fit the data. And we knew that was going to happen because it's empty. So it doesn't fit the data. So that's where we would go. That model fit lecture made us talk about, we wouldn't want to consider this model because it doesn't fit the data well. We can go a step further. We can actually talk a little bit more about the model fit indices, but I'm going to stop that for right now. Go back to that model fit lecture if you'd like to talk about those and see that. We'll also talk about that in the path analysis lecture slightly when you get to the next week. For right now, we're just going to focus on this likelihood ratio test. Any questions? Yes? Mm-hmm. Yeah, so think of it this way. If you have 5 variables, you have a 5 by 5 covariance matrix. So if you were trying to find the correlations, right, you find 5 by 5 correlation matrix. There are 5 variances down the diagonal, and if you were to count up all the things in the off diagonal that are unique, so the lower triangle, there would be 10. Does that make sense? So think of it this way, right? How many correlations do we have? So covariance and correlation are the same number, right? We have every pair of correlations possible. And the way you count that, if you remember combinations in math, there's the thing that said 5 choose 2. If you've heard that. There's actually a formula you can use. 5 times 5 minus 1 over 2. Or, if you really like to look at it, if I do this, if I just take all the variables we have in our model, this would be just make sure hang on just one second. There we go. I'll make sure I have the right names here. You don't see values here because hang on. The missing data by default throws out everything. There we go. So now how many unique covariances do we see here? Down the diagonal, 1, 2, these are variances. 1, 2, 3, 4, 5 variances, 1 for each variable. In the off diagonal, we have 1 here, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 numbers. Does that give you a little bit more context where that comes from? A little bit? So just think of it this way. What the model wants to do, what we need to do for this model to fit, is to get those numbers out of it, right there. Right? So how do we get to count this up, the saturated model is estimating every one of these off-diagonal values right here. Right? All the diagonal values, and it also has the means involved as well. Let's see if I have it here. Here is the covariance matrix that the model thinks the data has. This is the function that says fitted. So here is what we find. The variance of performance is 0.742. So you can see there's subtle differences between. I have the order different. But you take a look at what our model has. It's got a bunch of zeros right here. Because we put 0 beta weights on each of our variables, it's like saying each one of our covariances down here is equal to 0. Clearly that's not realistic, right? Does that help? Okay. Other questions on that? That's the key. Sort of counting up what's going on is the key, and we have to figure out that the model, when we look at this covariance matrix here, let's just try to disentangle it. This is what the model thinks the covariances are. In the top part of this, you'll see this is the variance of performance. This is the variance of usefulness. And this off-diagonal number 6.847 represents the covariance between performance and usefulness. Right? Why that's there is because in our model we said put a covariance between performance and usefulness. They're both endogenous variables. We told it to put a covariance there. It estimated the covariance. Now, we go down and look at the other covariances in this. This bottom part here, we have female CC10 and female by CC10. That section, these are all the exogenous variables. And by default, it's going to estimate all of the covariance it possibly can with them. Right? So it's estimating the covariance between all three of these. Now that covariance, it's really hard to interpret, but we could turn it into a correlation, but let's just say that the number there being not 0 means there's a correlation between these variables. So our model is trying to do that. So there we go. There we go. So we can look at our numbers. You can submit this to the path diagram software. SemPlot, by the way, if you tried installing that, it takes like 20 minutes or 30. It takes forever. It lists every one of the possible packages it works with as a dependency, which means it tries to install every single one of them with it. It takes a long time. So anyway, here's our path diagram. We see here each of the direct effects has a 0 coefficient for it, and that's because we put zeros for all of our predicted variables. Predictors. We have 0 beta weights. We have our residual variance of usefulness, a residual variance of performance, a covariance between the two. And we also see those same variances and covariances between the exogenous variables on the left-hand side of the diagram. Questions?
So you say variance means residual variance.
That's right. Really, because we have no predictors, it's just the variance. Once we put the predictors in, it'll be what's left over after we predicted things. It's residual, it's the variance of errors, yes. So, this is hey, I foreshadowed this. It's like I put these slides together. It's like, why I can't remember that while I'm just running my mouth talking too much, I don't know, but there we go. So why I'm talking about this part of it is really it starts to foreshadow what model fit's trying to do. To be able to use, there's these two different values here. I use cov to give the covariances for you, but I could have used, in Lavaan, there's a function called inspect, and it says take our model and figure out SAMPSTAT H1, which really means the covariance matrix it thinks our model has. You will note, for instance, that the covariance here in our data is different than the covariance that Lavaan thinks in our data is there. Anyone want to take a guess as to why? Missing data. In the covariance function up here, to make all the numbers show up, I had to use pairwise complete observations, which means it throws out a pair of observations if it's not there. This covariance matrix that you see down here was estimated with maximum likelihood, meaning all those observations were kept in the analysis. So what maximum likelihood gives us, or any likelihood-based method that keeps the observations in the analysis, allows us to have the protection of something called missing at random for our data. It's a better way of looking at data that are missing. So that's why these numbers are slightly different, because these numbers up here just sort of ignore the missing data, which is really bad. It biases results. It may end up not being accurate, whereas these numbers are a little bit more accurate. So I like these numbers better. This is the maximum likelihood-based estimates. That's why they're different. But this is the target. This is what it thinks our covariance matrix is in our data. We want our model to look like that. But our model looks like this. You see the big difference? Where the zeros aren't zero down here, right? That's the key. So for us to believe the model, now this is an empty model, so we don't really have anything to discuss. It's just got summaries and whatnot. But for us to really want to use this, if this were our actual analysis model, we'd have to stop and think, wait a minute, we need what the model is saying the covariance is to look like what the data covariance is. Weird, huh? Let me talk about that again. It's kind of a key part of what we're doing here, right? So, this inspect function in Lavaan gives you the ML estimate, the maximum likelihood estimate of the covariance matrix from your data, right? So this is the answer key. That's what Lisa calls it. The answer key, right? That's what your model needs to look like for you to be able to use it. Your model still may not be very interesting still, but just to be able to use it and talk about it, it's got to look like the answer key. And that's the key about that. This is the multivariate. This is the kind of the weird thing about multivariate models is we need our covariance matrix to look like that. That is the saturated covariance matrix. That's what the data covariances are. Does that help a little bit? Now our model somewhat looks like that. I mean, take a look at the diagonal, right? You have a 34.6 here, a 34.6 here. Right? Some parts of it look very similar, but there's a big sections of it where there's zeros in our model, but there's not zeros in our data. And sure enough, wouldn't you believe it, those sections are going to get filled in when we start adding our regression weights, our beta weights to our model. But all those model fit statistics, everything that you would see that come out of M+, M+ also, Lavaan and M+, and Amos and whatever package you want to use, the core of what it's trying to tell you is what you're looking at right here. The model matrix up here compared to the data matrix right here. So our multivariate model, even though we don't really know what's happening, I didn't give you the matrices. If you're really interested in the math behind it, I'd be happy to share like the matrix algebra to show you how you take this. I take that as a no. I used to have, if you want to see how ambitious or like, you know, like dedicated to the matrix algebra cause I was, go look at my notes from University of Georgia in 2011. There's matrices in there. Yeah, my students really love me. I tried to take it off. But the point is, where the numbers come from the model, you don't have to understand the matrices. You can just take a look at that. And with some understanding of what the model parameters are trying to describe, you'll understand what's going on with the model fit as we get better. Okay? Does that help it describe it a little bit better? It's a little weird, right? But that's kind of the first precursor. And we know this model is empty models aren't going to fit the data well, particularly in this situation, because we've got all these covariances that are not in there are the covariances between our endogenous variables, or our dependent variables, and the covariances and the exogenous variables, right? And the only link that we have between the two are the beta weights. It's the only way that we can go and describe those covariances between the two of them. Okay. So, sure enough, there is another type of matrix that M+ can give you, and that's called residuals, right here. And of course, type equals raw, which really has a bad connotation, I think, as well. Raw food, right? Although some raw foods, like I think of carrots. Carrots are good, right? Oh, sorry. You're talking to a guy whose 3-year-old likes Peppa Pig and only eats carrots, but that's a big, significant step ahead from where I was like 6 months ago, or where we were with him. Anyway, kid will gag on broccoli. I kid you not. Like, he will take a bite, and if he realizes it's broccoli, he'll almost literally hurl, and then start raking his tongue. And it's all because of the texture for some reason. So anyway, think of raw residuals, I think of carrots. And carrots are good for you, and so are the raw residuals. What you want to see in the raw residuals, what is the raw residual? It is the model predicted matrix minus the data matrix. Okay. So when we see zeros down here, that means our model fits that covariance perfectly. Right? And take a look in this raw residual part. The zeros all show up for the exogenous variables, and that's because they are saturated in our model. So therefore, they are perfectly fitting. It's pretty much zeros up here for our endogenous variables. It slightly differs there. But you see the biggest discrepancies we have is between, actually I got it wrong, it's our data's covariance matrix minus our model covariance matrix. But you see the biggest numbers we have here show us how far off we are with this. It's how far off we are from the right answer, right? So we need to fix that. Is this helping a little bit work through it? So everything that you do in model fit, by the way, when it comes to path analysis, anything that you do in model fit, path analysis, structural equation modeling, and confirmatory factor analysis follows this same method. So everything you're learning right now, if you take a factor analysis course, or if you just go find my notes online, or someone else's, all of it relates to this. The factor analysis implies a covariance matrix. It compares it to what the data has, and it tries to tell you how far off you are. And if you're off a long way, you can't really use it. It's not really valid results. So that's sort of what the logic is. It's a multivariate model. All right. Now, I went through the methods of modeling, examining model fit before, but I'll just briefly touch on it now. We really need to double check model fit is the main thing. All this section, by the way, all of this is stuff you saw before online. So I'm going to skip that right now. So we're going to add predictors to the model. Yay. Finally, what this class is about. Multivariate models with predictors. Darn it. So let's go to Model 2 syntax. Right here. Now what you'll note in my Model 2 syntax is I changed the 0 to a value that has a label on it. And why I did that, what happens when I do that is, first of all, when it's not a number, it doesn't fix the beta weight to that number. So if I put, 10 star female, it would give me a beta weight of 10. I don't want that to happen. What I'm doing is putting a label to it because, sure enough, when we have interactions in our model, we may want to talk about the simple main effects or the effect of parameters. We have to take those beta weights and do things with them to interpret the interaction or the main effects underneath the interaction. But for right now, let's not do that. Let's just talk about adding the model parameters in. And ignore this section of the code just yet. I'll get back to that. I'm going to run model 2 syntax. The only difference in my submission to the SEM function is instead of model 1 syntax, it's now model 2 syntax there. So it will run that. And following along here, which model fits better? All right. We have model 1 that had these exogenous variables in where we fix the beta weights to 0. We have model 2 where we estimate them with what the model thinks they should be. Which one do you think worked better? Model 2, right? Hopefully. Yeah, there's something else wrong. So let's take a look. The way we can check is to use a likelihood ratio test. Our models are now nested. So the likelihood ratio test in Lavaan works with our favorite ANOVA function. That's nice, at least. The rest of it may be confusing, but at least we can compare models with ANOVA. When we do that, it tells us what? It tells us, here's the information for model 2. Here's the information for model 1. The chi-square difference is 22.204 with 6 degrees of freedom. And the p-value is very small. So in this setting, the model with more degrees of freedom in this output is the null model. So our null model is model 1. Our alternative model is model 2. So this p-value being small says we reject our null model. We reject model 1. When we reject model 1, we say that at least one of those betas is not equal to 0. That's what we're getting out of this. It's pretty interesting, I think. Somewhat, maybe. Interesting, like for me. Right. I get it. I'm not wired the same way. I totally get it. Probably don't want to invite me to your parties. Start talking about estimators and matrices and whatnot. Not good. Hey, does anyone recognize these numbers from anywhere? .204, 6 degrees of freedom. Sure enough, what we're going to find out is that we just estimated the saturated model. We'll get there. Let's take a look at our analysis. We know model 2 fits better. Let's take a look and see what happens. The null model here again, the null model was model 01. The alternative model was model 02. The null hypothesis was that all betas equal to 0. The alternative is at least one beta not equal to 0. I don't know how to do that here. Not equal to 0. There we go. So, we saw that. Let's take the model fit now. Okay, so we go to our model fit. We use the summary statement to look at our results. Let's look at model fit in an absolute sense. We see that there are 0 degrees of freedom for this likelihood ratio test. 0 degrees of freedom there. I believe I talked about this in our model fit lecture in absolute. It means that we have fit a model equivalent to the saturated model, which means we absolutely have to fit our data. There is no discrepancy between what our model thinks the covariance matrix is and what our data thinks the covariance matrix is, because we've estimated enough parameters to recover the data's covariance matrix exactly.
In other words, is it a perfect?
It's perfect fit. Now, it's not really a coincidence, though. Whenever we have this multivariate regression where we have a bunch of exogenous variables and they're all predicting each endogenous variable, we're going to have perfect model fit.
Can you please conceptualize what perfect model is?
It means that the number of parameters in our model is equal to the number of unique variances and covariances in our saturated model, the data. Right? So if you think about when I showed these covariance matrices before, and I said there were 10 unique covariances, 5 unique variances, we saw actually that there were 6 zeros for covariances before. those corresponded to the 6 degrees of freedom of that test. And sure enough, we added 6 beta weights to this model, which meant we estimated as many parameters in our model as we had in our possible in our data, right? So we're going to get the right answer. We're going to have the answer key. So why I'm making a big deal about model fit before I talk about the results even is model fit is like the gatekeeper of whether you can go in and talk about the results. Right? If the model doesn't fit, the results really start to become questionable. They're not really valid. Yeah, Ryan.
The ANOVA function that we wrote for this, was that not a test of model fit, but like you said, that one of the betas has to be significant, so should we not do that for
Technically speaking, this was a special case of models where I probably should have done this second. But absolute model fit has to come before relative model fit. And so what I mean by that is that the numbers that you see in the summary statement compare your model to the data directly. The numbers that you see from the ANOVA function compare your models 1 and 2, but not to the data. And it's possible that model 1 and model 2, neither of them look like the data. So it really draws into question why you want to compare them. It's like 2 garbage models, which is the worst of a bad idea, right? Sort of like voting in most of our elections. So, does that sound like, maybe that's not right? I'm hoping we get a new wave of better candidates soon, though, because everybody's really pissed off right now. Yes, Nate. No, this is not endless. Please ask your questions.
Does that mean if the degree of freedom is not equal to 0, then we don't bother reporting?
No, that's not true. If the degrees of freedom are not equal to 0, it just means we have to pay very close attention to the numbers in this section of the output first. We have to make sure that these numbers indicate good model fit if the degrees of freedom are not 0. And we'll have, that is exactly where we go with what we do. So it's one extra big laborious step to look at the analysis ahead of time. But 0 being there, when we see a 0 there, it sort of releases us. Because all the numbers we'd look at, and what I look at are this p-value that you'd normally see from this test statistic. I look at the RMSEA. We want this to be less than 0.05. 0 is perfect. It's perfect. We look at these CFI and TLI. 1 means they're perfect. They're perfect. So what we end up having here is perfect model fit. And when we have perfect model fit, means the results will be, we can look at the results as if we were just doing a univariate regression, univariate linear model. Because in the univariate linear model, we always have perfect model fit. That's right. Now they will try. Now let me take a little segue here real quick. I've dealt with this even just this last month on a paper that I'm on, like as someone helping in statistics. When you get this, reviewers might say, there's something wrong with your model. You shouldn't be doing that. There's nothing wrong with our model. We're doing 2 linear regressions simultaneously. They don't fully understand this. The way you describe it is that we're fitting a saturated model. We have good model fit. But good model fit, or perfect model fit, is not the story that helps describe what we're doing here. The story is not told by that. The story is told by our regression weights, our regression effects. Right? It's very possible we have great model fit and all of our betas are statistically no different from 0, meaning we have no story to tell. But model fit is just the entryway to talking about results. So you may have this somewhat misunderstood by those who are not doing this every day like I am, which pretty much is everybody, right? Not a lot of people do this every day. So it does take a little bit of explanation, a little bit more than what you would have with your typical regression model. But the way I would say is effectively we took our 2-variable regression and we made it look like our 1-variable regression. And in the 1-variable regression, we never had to consider this for that reason. Does that help? Thanks. I do like the questions. So there's no question. Adrian.
So besides when we set a beta weight equal to 0,
Mm-hmm.
would we not have a separated model?
In the models that look like this, this example set up here, and actually when we have the homework, it's going to be very similar to this as well. when every endogenous variable predicts when every exogenous variable predicts every endogenous variable, we will always have perfect model fit. When you don't have that case, like if we had said, you know, I don't think college credit hour predicts usefulness. All right, so now we take college credit hour off and we take the interaction off. Then now all of a sudden we don't have perfect model fit. We'll have 2 degrees of freedom actually. And because of that, we'd have to look at these numbers. That doesn't mean it's bad. In fact, we probably have really good model fit. But that's one of the cases. The other case is if you have this big path model right here, the one that I had, the big one that I showed with the slide, I don't want to jump back to it. That one does not have perfect model fit either. So I'm trying to structure what I'm introducing to you here where we don't have to worry so much about model fit. In the path model lecture, I sort of go overboard, checking model fit, tweaking the model, checking model fit, tweaking the model. So you're going to see a little bit more of me doing that there, which is probably, I don't know, it depends on your research question as to whether you'd see that or not.
So if you're running 2 linear regressions simultaneously and you have 1 variable missing, that's like predicting performance but not usefulness, that's when you would have
That's right.
a saturated model.
That's right. Yeah, when not all predictors predict all the variables that are dependent. Other questions? Okay, we're at time for a break. Let's take 10 minutes. Think that over. Saturate your drink. I don't know if that's a good word. And we'll come back and talk a little bit more about this in just a moment.